Hello and welcome to the Stratasys Sessions, a series of webinars intended to educate and empower you to incorporate additive manufacturing into your business. My name is David Dahl, a senior research engineer at Stratasys, and today's topic will be about how to adopt FDM, which is a type of additive manufacturing, onto your factory floor. This is an area I've spent a significant amount of time working on, and I think it provides tremendous opportunity for those in the manufacturing sector, especially as businesses are under constant pressure to optimize their lines, scale up and scale down based on demand, retool for new products, and ensure their production experiences no disruptions. FDM provides many great solutions to these problems, and by the end of the webinar, I hope that you will see the value that it can bring to your operations as well. Today, I'm going to quickly discuss what FDM is, and then we'll talk about the current state of tooling, followed by which FDM materials are best suited for tooling. Then I will talk about how to design your tools to optimize the technology of additive manufacturing. Then I'll provide some examples of metal forming tools, and then we'll conclude with two examples in the automotive industry where tooling is having some significant impacts. At the end, we will open up to questions, so please send them along as we proceed in the webinar. Now, FDM, like I said, is a type of additive manufacturing. It stands for Fused Deposition Modeling, a technology pioneered by Stratasys. And I like to describe it as a robotic hot glue gun. So in the example you see, or the image you see on the webinar, you have two nozzles, and each nozzle has a thermoplastic filament that flows through it. The blue is what we call the model, which is real thermoplastic, and then the yellow is what we call our support. The reason we deposit support material is to ensure that the part is dimensionally accurate and doesn't experience any overhangs or any areas where the material just can't build upon itself, as you see in the image right there. Once the part is done printing from the bottom up, the support material is removed either by dissolving it or physically removing it. Now, let's take a look at the state of tooling today. So those of you that work in the manufacturing sector, this is nothing new, but a lot of it revolves around subtractive manufacturing. So your CNC machining, a lot of metal forming, in many cases injection molding, and a lot of welding. And the most common materials that you'll see are, it's nothing new: aluminum, steel, Delrin, ultra high molecular weight polyethylene, nioil, nylon, which can have glass or carbon fiber reinforcement. And in many cases, for specific industries, you'll have fiber reinforced composites as well. Regardless of the method in which you're making your tools and the materials involved, there are several pain points that can be shared across the board. So beginning with, a lot of times these are expensive to manufacture. Unlike most manufacturing products where as you scale up, the cost goes down, most tools only need to be made once or twice or a limited amount of time. So it can become very cost prohibitive to create these tools, and oftentimes you're not given the benefit of designing to the operator or the application. You have to make do with what you've got just to remove the reduce cost. Furthermore, there are many long lead times, and it's very common to see tools that will take 4 to 6 weeks to manufacture for several thousands of dollars. And then also you have high inventory costs. So you need to store these tools when you're not using them. If you're rerunning a new line and you need to do a certain product line that requires a special tool, you might only use it for a few days a year, but you still got to store it all. And then, of course, in terms of functionality and sourcing it, if your tools are made in one part of the globe and your factory's in another part of the globe, it can be really hard to just get the tools to where you need them. And furthermore, if you're using metallic tooling, it's really heavy, and there's a big cost associated with safety and ergonomics as your operators are constantly using them on the floor. Now, one of the things that additive manufacturing and specifically FDM can do is it can reduce a lot of these tooling pain points. You can design tools that are custom to the operator, and you don't need to worry about storing them in a warehouse because you can print the tools on demand. So oftentimes these tools can be printed in days or weeks versus months at a fraction of the cost, and they can be tailored to the product or the operator or both. Now here's an image of a traditional factory floor. I know that they might be different based on where you're located and what your product line is, but in general, this is kind of the main steps. And as you can see, there's a lot of opportunity for tooling across the whole space. So, if we walk through from shipping and receiving to incoming inspection, assembly, kitting, quality, even the tool shop, tools are used everywhere, from things like surrogate parts, drill guides, test fixtures, ergonomic aids, end effectors, kitting trays, etc. And my challenge for you as we walk through how to adopt FDM into your factory floor is what types of tools are causing the most pains in your process? So what are the tools that you only need one of, or they're too expensive to fabricate? Or what are the tools that tend to break a lot? Or what are areas where you're not using tools right now and you could print a tool and it would improve your processes by a tremendous amount? So these are things to think about as we walk through, but the slide here is just meant to kind of remind you of just the variety of tools that you'll see in the factory. Here is a chart of all of the FDM materials that Stratasys provides, and they're broken up by performance. So as you can see, it's broken up into 3 buckets. We have our standard materials, we have our engineering grade materials, and then we have our high performance. And then you can see the characteristics associated. Now, many of them are strength and toughness and mechanical performance, but there are others, and especially as you get into the more engineering and high performance materials, that offer characteristics that are equally as important, but it's not just mechanical strength. So things like chemical resistance, FST, flame smoke toxicity resistance, whether it's ESD or electrostatic dissipative, is it biocompatible, things like that. So, don't look at this slide and say, well, I need high performance all the time. Design around what you need. If you need a tool that just needs to be a certain color, you can go with the standard ASA color, which we'll talk about in a second. But the materials highlighted in red are the ones that we're going to focus on today. So these are the materials best suited for tooling, and you certainly can use other ones listed on here as well, but the ones that we're going to talk about in the next few slides are the ones that I think will be most applicable for your own process. So let's start out with ASA. ASA, like its cousin ABS, is a good low-cost thermoplastic. It's just a good run-of-the-mill material for many applications. It comes standard on all of our printers. It has fairly decent mechanical properties. It doesn't experience temperature very well, so if you have a high temperature application, it won't work well. It doesn't have the chemical resistance of nylons and some of the more exotic materials. It does outgas, unlike some of our PEC-based materials, but believe it or not, 90% of the time, ASA is a great material for most of your tools. And some of the examples are check tools, inspection fixtures, drill guides, ergonomic aids, masking fixtures, things that will probably not have a lot of load applied to them. They're more for holding a part during assembly, and things that won't be experiencing, extreme conditions, like I said, elevated temperature, exposure to chemicals, things like that. And the reason that I say that this is a great material is because it's a low-cost material compared to some of the other FDM materials. And you may be asking yourself, why would I use ASA over ABS, which is very common in the maker space? And I like to use ASA, and Stratasys has been promoting ASA because it has better UV stability compared to ABS, and it also prints a little bit better, and it also has more vibrant colors. So one thing that I tell people is that ASA is great for color coding. So as we optimize our processes with Six Sigma and some of the other manufacturing optimization techniques, color coding is a big deal. So all of your drill guides can be blue, all of your inspection fixtures can be red, or you could just color code them based on the operator. So David's tools are green and Jacob's tools are purple, things like that. Next up, we have a slightly more exotic material. This is ABS ESD7. So as I mentioned, ABS and ASA have similar characteristics, but this ABS ESD7 has carbon nanotubes inside of it, which makes it good for electrostatic applications. All of the mechanical properties will, like I said, be very similar to ASA, but with the ESD capabilities, you can now create tools that will be used to assemble products that are susceptible to electrostatic shock. So in the example you see here, this is a little soldering tray. So it's great for kitting trays, soldering trays, organizational aids, things like that. Now we do have a data sheet on all of these materials on our website, so I won't go too in depth on the material properties and characteristics, but As you can see, we've listed the volume resistivity and also the surface resistance in the middle part of the screen right here. So if you assemble electronics and you're not going to, again, not expose your tool to chemicals or things like that, this is a great material to ensure that you're not going to accidentally shock your parts. FDM TPU92A. This is one of our newer materials, and this is Stratasys's first forte into the thermoplastic polyurethane space. So for those of you that don't know, aren't well versed in this space, all of the materials that our systems, our FDM systems extrude are thermoplastics. Now, thermoplastics in nature are rigid, and they can they flow once they're heated up, so they can melt and flow like a hot glue gun. Thermoplastic urethane is still a thermoplastic, but having the urethane component to it makes it flexible, so it's more of like a rubber-like material. Now, 92A is the shore hardness, to give you an idea of where it is. So it's not as flexible as, say, a rubber band. It's more on the firmer rubber side, but it still makes it really good because you can use it to flex and mold around certain components. So in this image right here, this is an alignment tool for a badge on the fender of a motorcycle. Now, one of the other great features about having TPU is that it doesn't scratch or mar your parts. So if you're assembling something that has a Class A finish, like on a car or a motorcycle or a bicycle, you can feel comfortable knowing that this material can touch the surface of your part and not scratch it like some of the harder materials might. It also has a high elongation. So there are certain applications where if there's a lot of wear and tear, or it's going to be used a lot by an operator, the part isn't going to be susceptible to cracking or snapping because it's not brittle. So again, I would recommend this for a lot of masking fixtures, alignment fixtures. Safety guards is also another great area. We often forget that safety is just as equally important for the tooling space as the assembly. So consider using TPU92A for some of your safety applications as you walk around your factory floor. Duran 410 MF07. This is one of our newer materials that launched in 2019. This is a material that's designed to be a good general purpose tooling material for the factory. Duran is a naming convention created by Stratasys, and then the 410 stands for a nylon-based material, and then MF is mineral filled at 7% by weight. So what this means is that Duran, as we call it, is a mineral filled nylon. I believe it's nylon 6, if you're wondering. And the mineral filler creates a lubricious, low coefficient material, but it still can withstand some of it still has the chemical resistance and toughness found with nylon. So this is a good, if you need something with a little bit more performance than, say, ASA, Duran is just a good material that's a little bit of a step up for it. So to inspire you to think about where to use this in the factory floor, think about things like alignment fixtures, drill guides, end of arm tools, masking fixtures, safety guards, kitting trays, check tools, anywhere that a tool would be used that would experience a lot of abrasion, a lot of components. So if you're using this tool multiple cycles per day, if there's some sliding, not like a linear rail or anything, but if there's something that needs to go down or experience a lot of friction, this tool right here, for example, it's kind of hard to describe, but it's used to pressure test a manifold. So a small tube is attached to the top part of that tool, and then it's pushed down a 14-foot pipe, which is that half circle shape on the bottom. So there's a lot of friction as this tool is pushed down the 14-foot length, which is where the Duran low coefficient of friction properties come into play. Polycarbonate, this is a good kind of middle of the road if you have some more exotic applications. So polycarbonate, this is actually a blend, so it's not pure polycarbonate, which makes it a little bit more brittle, but what it does lack or what it has in some of the brittleness, it makes up for in its temperature resistance. So this material is capable of temperatures up to 250 Fahrenheit, and it does have a lot of the strength. It has a higher strength than, say, ASA or ABS. So if you are in a factory and you need something that needs to go up to a little bit higher temp, but you still need some strength, but you don't want to, you know, go with the super exotic materials like Ultims or PEX. Polycarbonate is a great middle of the road material. Again, it can be used anywhere. Test fixtures, end effectors, safety guards, ergonomic aids, welding fixtures, things like that. But like I said, this is great if you're considering using ASA, but you need that higher temperature resistance. You need just a little bit more strength out of it. And again, our data sheets will elaborate on the actual mechanical properties for all of these materials, but this is just a good rule of thumb. And finally, we have nylon 12 CF. This is by far the most popular tooling material we sell and offer, and it's the one that adds probably the most value across an entire factory floor. So again, this is a nylon 12. The CF stands for chopped carbon fiber, and the fibers are 1 millimeter in length, and the loading is 35% by weight. So what this means is that you have a really high stiffness to weight ratio material that's also very tough and has the chemical resistance found in nylon. Also, from just like an additive manufacturing and FDM perspective, the fibers actually allow for really great printability. One of the things I didn't touch on in the earlier slide about FDM was that printing thermoplastics is really challenging because they're susceptible to warp and curl dimensional inaccuracies that you don't find with metallic tooling and CNC machining. And that's why we print all of our materials in an oven to minimize those effects. But adding carbon fibers to the material and reinforcing it improves the printability and improves the dimensional accuracy. And it just is a really good, well-rounded material. This is a material that you're going to want to use if you have something that has significant loading on it. So end effectors, you know, test fixtures, safety guards. Again, you know, it sounds like I'm kind of repeating the same tools, but the truth is you need to design around the application. So nylon 12 is probably our stiffest and highest strength material in some of the engineering grade materials. And I have a table on the next slide to demonstrate that, but this is just a great, great, great material. This chart right here, I've created to kind of give you a high level overview of some of the mechanical properties, and I've highlighted the key attribute in blue to make it a little bit easier. So if we go from left to right, with FDM TPU, as you can see, it has the highest elongation. So if you need something that's stretchy, something that won't scratch your parts, TPU 92A is great. If you need something that has multiple colors, ASA is perfect. Again, it's a good middle entry-level material, a good baseline. But I know that as manufacturing spaces get more optimized, having those colors available is a really big deal because then you don't have to paint the parts and all that stuff. If you need something that has ESD properties, ABS ESD7 is a great option for that, especially if you're doing soldering trays and any inspection with electronics. Duran has great impact and a low coefficient of friction properties. Polycarbonate has a high temperature capabilities and some elevated strength. And then finally, nylon 12 CF, you can see has multiple properties across the board. So it has our highest tensile strength, it has the highest flexural modulus, it is a high HDT, so it is very temperature capable along with polycarbonate, and it is ESD safe with the carbon fibers impregnated into the resin. So if you're thinking about your factory floor, again, design to the application. It can be tempting to just pick one material or the other, but the truth is some of the flexibility and the versatility of this technology is that you can print a TPU part one day and you can print a nylon 12 CF part the next day without having to significantly retool your printer. Now let's shift gears a little bit and talk about designing for additive manufacturing, or DFAM as we like to call it. One of the things that customers will always tell me is that they want to get into additive manufacturing. They keep hearing about the buzz. They don't know what to do. They bought a hobby printer and they printed some parts and it just didn't work out well. They couldn't see the value in terms of cost, lead time savings, etc. And the truth is that you need to think differently about how to design your tools. It's so tempting to take a tool that will traditionally be CNC machined and just print it. And that's a total waste because you're removing material as opposed to putting it only where you need it, which is the key benefit of additive manufacturing. So when I talk to customers, I tell them put material only where you need it. And there's a few tricks and tips that will go a long way in this process. So first of all, be mindful that the tools, and I'm kind of working from the bottom up on the slide, but the tools can be printed solid or sparse, and sparse just means a honeycomb infill of different patterns and geometries based on strength. But you can print the part solid, which would use the most amount of material, but it will also have the highest strength, but it also has the highest cost associated because you're printing a lot of material, which takes a lot of time. Whereas on the other side of the spectrum, sparse, you're printing less material because a lot of it will be hollow on the inside, but you're also sacrificing strength, but you're making up for it in cost and lead time. So there is a balance to it. Some other things you can do in the upper right is you see these are actually composite tools. One we call it shell, the one's called sparse. And shell is basically the profile of the part that you need. So, and we've extruded it by 3/10 of an inch. So when you're designing a drill guide or a trim tool, design it like a shell tool. You just need to take the profile of the surface and then just thicken it a little bit. And that should be more than acceptable for what you're doing. If you have something that needs to hold something, or it's something that needs to cradle something, or it's going to experience a little bit heavier load, I would recommend printing it sparse. And this is just the outer profile of the part with an infill pattern that is tailored to your application. In most cases, the hexagram infill is our strongest. It's very similar to hexagonal. And then, of course, you can print solid, but I don't recommend it unless you absolutely have to. Other things to consider too, the orientation of the part is very important. So as the parts build from the bottom up, you have that thickness or that step, which can cause surface imperfections. We call that stair stepping. So if you look at the green image right there, that part was printed vertically, and you can see how smooth the contours are. Whereas if you printed that same part in the horizontal orientation, you'd see all sorts of stair stepping. And so it's just important to consider what surface is the most important. Now, with tooling, it doesn't matter as much because the aesthetics aren't as important as the function and the performance of the part. But if you have something that needs to contour to a part or a tool very carefully, be mindful of the orientation of your part. But ultimately at the end, and I want to point to the bottom, design for your application. There is no one size fits all. And as you start exposing yourself to more FDM applications and materials and capabilities, you'll start to pick it up really quickly. Other things. So as I mentioned, there is a step associated because we're extruding beads of thermoplastic. So the surface finish may not be acceptable for what you're doing. In general, FDM parts are inherently porous from the image you can see on the upper right, and there's going to be a perceptible build layer. So just to give you a ballpark number, out of the printer, you're looking at a surface roughness of almost above 200 microinches of RA. Now, fortunately, there are ways to bring this down. You can manually abrade it, so use a sander, you can tumble it, you can media blast it, you can machine it. I wouldn't recommend it because you're detracting a lot of the value of printing the part in the first place. And you can also add coatings. We have all sorts of literature and design guides on this. If you need the part to be sealed off and eliminate porosity, you can coat it with epoxies. There's a whole composite tooling design guide that my team and I have published that walks you through a step-by-step process. And I'll talk about where to find all this material at the end of the presentation. Another thing to consider is how to minimize or optimize your part. So once you've designed your part to print, there are all sorts of little tips and tricks you can do to optimize it even further. And in general, what I tell people is 45-degree angles are your friend. Now this depends on the material, so it's really 40 to 50 degrees of angle, but the general principle is that there are certain geometric features that are self-supporting, and it means that you don't need to use support material. Now, on average, every layer of a part that uses thermoplastic model and support, you're adding about 30 seconds per layer time as the material switches back and forth. So if you can minimize that, you can cut down on your print time significantly. These images right here give you an example of that. So on the left, we have some holes of different shapes. We have a circle, the rectangle, the diamonds, etc. Now pay attention notice that the 45-degree angles on the two on the right, they don't need support material because it's a self-supporting angle. It naturally prints over itself without any hang or slag like that. Now, if you have an extruded part, you'll need to be mindful of that because you'll have a part that's coming out of the printer, not cutting into a hole. So you will need to design not only a 45-degree angle in one axis, but also the other axis to bring down the, to eliminate the need for support material. But in general, if you have a hole or a feature like that, I would recommend printing it with a diamond and then drilling it out later so that you can save cost and save time printing the part. Other things that I think are often overlooked with tooling is labeling. So it's really expensive and hard once you've machined out your tool to etch in the label and make sure it's serialized for your process. You can add that all in using FDM. A word of caution though is be mindful about how you're doing it. So again, orientation plays a big deal, like I said. And then also the font, you're starting to approach on the limits of FDM because you have a bead that is a certain profile, and then you have text that is a certain profile. So, you know, in general, use very forgiving blocky fonts. Go as big as you can. I would recommend recessing it into the part 3 to 5 millimeters, and that way you won't need support material. And if you put it on the side of the tool printed in the vertical orientation, as you see on the bottom left, it prints far better than in the horizontal. And this is just because the material, it just won't fit in some of the features of the text. So, you know, imagine taking a big Sharpie marker and trying to write a really fine, you know, cursive letter. It's just not going to look great. But if you use big blocky letters and things like that, you can actually get a really good text and other fine features that come out of it. And alternatively too, you can just design in a recess and then just stamp out like a metal plate and just bond it in as well. That's what a lot of customers I've seen do if the text doesn't come out just right. Inserts are also important. So with every tool, you're going to have some sort of insert or some sort of guide or something like that. Now, thermoplastics don't do well with metallic abrasion. So if you have a drill and you just put a hole in an ASA part, the drill is going to rip up the ASA right away. So one thing you can do is incorporate inserts in your tools. So there are a few ways to do this. You can bond them, you can heat stake them, you can press fit them. More often than not, I would recommend undersizing the hole by a little bit and then either drilling it out or reaming it and then bonding it in. I did a study on some of our higher temp materials, again for composite tooling, where we put some bushings and inserts into a part and had the insert stick through the part out. And we ran it through an oven at an elevated temperature to just see if, oops, my computer wants me to restart. I will not do that. Hang on one second. Sorry, like I said, we ran the FDM part with the bushings and inserts through an oven cycle to see if they were dimensionally off or they flowed or anything like that, and the data showed that they did not. So once you insert your part, you can be assured that if you have elevated temperatures, your bushings aren't going to be significantly dimensionally off axis as you thermally cycle your tools. Now, speaking of inserts, there are a few to recommend and talk about. This was a study we did last year. And again, what you're doing for your process will depend on the type of insert to do, but we have a lot of data behind this and I can provide some recommendations. So in general, heat set is the best. It has great torque out and twist out performance. The downside is you need a soldering gun or some sort of heat press to install it. But this is great for critical fastening applications, for something where you need to screw in a part to make sure your tool is aligned and things like that. Screw to expand, it's pretty good. It has great torque out performance, but it does lack in pull out performance. These are easier to install because you can thread the inserts, but it is a little bit challenging. And I wouldn't recommend this for high torque applications where bolts will need to be fastened and removed multiple times. Helicoils are great for low profile inserts. If you have a really thin walled structure or something, a helicoil is great because you can dial it in versus a heat set and screw to expand. You'll have a defined length of the insert. Like I said, these helicoils are great for minimal material areas, but it is hard to access them by a heat gun or heat press. And you can try drilling and you will need to drill and tap them prior to installation. So there is a lot of prep on the front side of a helicoil. Other inserts to consider, the last three, we have push to expand. So this does have slightly above average pullout and torque out resistance, but you do need special tooling, and it's not great for through-hole applications. So you need like a bottom surface to make sure it's aligned nice and square, and it can just be expensive and difficult to install. So we don't recommend those too much. Self-tapping, this is great. This is very common. It has excellent pullout performance, but you're going to get below average torque resistance, which makes sense because you're self-tapping it in. They're difficult to install for some of the harder materials like Nylon 12 CF and Ultim, which I didn't talk about, but it is pretty easy for soft materials like ASA. It can be hard to install self-tapping because you're doing it by hand, so you risk inaccuracies and making sure your insert is nice and aligned with the axis in the hole. And so it's not recommended for applications that require, unique angles or, a challenging angle or something that has a high torque out resistance. And then finally, we have the Twist Reset Hex. The manufacturer said these have good torque and pull-out resistance, but we discovered that neither of those were true for FDM. It had the lowest pull-out values and it had below average torque out resistance. The installation was quick and easy, but it requires an arbor press to install, which limits potential applications. So in general, stay away from those. And kind of going back to what I said at the beginning of these two slides, if you're wondering what to do, just go with the heat set and work your way back based on your performance and application requirements. Now, one thing to think about too is that if you're printing a tool that is not solid and it's sparse, and you have a bushing or an insert that is longer than the wall thickness of your part, you're going to need to find a way to add material around that to make sure that the insert is completely encapsulated in material. Now, this example here is for a composite layup tool that me and my colleague Ross worked on, and we created a method called creating a bushing plug, if you will. And this is what you're basically doing is you're creating a little pocket of material in your tool so that when you tap it out, it's like it's completely surrounded in material. Now, the alternative to this was you could thicken the wall of your part by, say, a ½ inch or an inch, but you're wasting a lot of material and cost and lead time. So there's a process in one of the design guides that will walk you through how to basically combine two different CAD files together to print a bushing plug. Now, fortunately, we also have software that does this for you, and this is what I would recommend. So Stratasys uses GrabCAD technology, the platform, and we have a processing software called GrabCAD Print. And within GrabCAD Print, there is a manufacturing jigs and fixtures application that you can use, and this allows you to tailor the performance of your part with an incredible amount of detail that you would otherwise have a very challenging time doing with old software. So to give just a quick overview of this, basically what it's showing you here is if you see the images labeled 1, 2, 3, and 4, those are different assembly parts of the tool, and you can click on them and denote what infill and strength and performance you want. So for example, number 1 is printed solid, number 3 is going to be sparse, number 4 is going to have a different style of sparse infill, and number 2 will have a different one. And you can also click on holes and type in the type of insert that you're going to be using, and the software will automatically undersize the hole. And if you want, it will print it as a diamond so that you don't have to worry about designing self-supporting angles. It will just automatically do it. It's a really, really powerful tool, and I highly recommend checking it out. It's if you go to GrabCAD Print online, it will walk you through all the processes. And like I said, this is a really powerful area to make the design a little bit more easy for you. Now let's jump into some real life examples. So obviously in the factory space, there's going to be a lot of metal forming tools, and in addition to jigs, fixtures, holding tools, things like that, you're going to have some tools that will experience some actual significant forces applied. So I have a few examples to walk through this to just kind of inspire you and show you what is capable of this technology. So the first one is a press brake tool. This was printed out of Nylon 12 CF. And the approximate size is 5 by 2 by 2 inches, and the forming tonnage is 9 tons of pressure applied. So we ran this tool for 500 cycles using 1.52 millimeter cold rolled steel. And after 500 cycles, the tool started to degrade slightly from 3.2 to 3.6 millimeters, so about 12% of change. But the tool didn't deteriorate significantly enough to cause any failure or out of tolerance of the part. So what this means is that, these tools are good for not just a few cycles, but you can get some serious cycles, serious tool life out of your tool in the hundreds of cycles if you need to run, a limited production of your part. And also, furthermore, it's worth mentioning that if these tools do break, you have the option to just reprint them in a few days at a significant cost reduction than your alternative methods. Now, switching gears a little bit, so stretch form tooling, a similar application. I will point out that the material is Ultim 985, and that's only because when we were working on this application many years ago, Ultim was the strongest material we currently offered until Nylon 12 CF came out. So I would recommend using Nylon 12 CF or polycarbonate, and I note that at the bottom of the screen. But for all intents and purposes, you can still see how this application performs. So this is a 10 by 13 inch tool with a 2-inch crown, and it used Ally 2024-0 material. And with stretch form tooling, the surface pressures were minimal, so you could get away with an even less exotic material than, say, Ultim or Nylon 12. And you can optimize it too, again, but it just depends on how much pressure is being applied. So polycarbonate, Nylon 12, even 985, Ultim 985, those are all great materials for this application. And then finally, hydroforming, tube hydroforming. Again, this was an Ultim material just because back in the day we didn't have Nylon 12 CF, but it was 16 gauge carbon steel with a 2-inch diameter. And you can see how the flames imprinted on the tool very nicely. So it came out really well. If you had something with a higher deformation, you need to consider some localized stress concentrations. But again, this just goes to show that even though your tools are made out of plastic, they very much can form metal sheet work or sheet metal with no problem. Now, the final one, and this is more relevant data and testing to give you an idea of cost and lead time. This is a rib hat channel. So this is a 6-ton forming tonnage, 6061 aluminum, 14 gauge. And we ran this for 100 plus cycles. Now, I haven't talked a whole lot about cost because it does depend, like everything else, on how much material is used, your cost of labor, your cost of utilities, things like that. So for discussion's sake, these costs come from the assumption that you own a printer, so it's a combination of the printer, which is amortized over a certain amount of years, and then the cost of the material, and then the print time. So you combine those numbers together and you'll come out with $133 if you printed this tool. Now, to give you a general ballpark idea, if you outsourced it or you even insourced it in some cases, you're looking at around $3,500 to machine this part out. And then in terms of lead time, you're looking at 1 day to print versus 21 days. So even if cost isn't a big deal and lead time is, additive still comes out ahead or vice versa. So it's just something to be mindful of when you're pricing out your processes. I tell people that additive is not going to replace traditional manufacturing or traditional tooling. It's just another tool in the toolbox for when you need to be a little bit more flexible in your processes. Now, to give you an idea of some of the performance characteristics of the rib hat channel, I apologize, the numbers on the right for the scale are very small, but it's in millimeters, and it's plus or minus 1/2 of a millimeter. So as you can see in the images across the board from 1 cycle to 100 cycles, the tool doesn't deform too much. It starts to go right around 100 cycles, and you're looking at about 1/2 millimeter of deformation. But the takeaway here is that these tools you don't just stamp them once and then the tool is completely useless. You can use it for at least 50 to 100 cycles, and depending on your requirements, much more than that. So this is a rib hat channel. The next one is a round rib. Again, it's plus or minus 1/2 millimeter, and you can see that in this case the tool starts to level out a little bit more in terms of the dimensional accuracy from 1 cycle all the way to 100 cycles. And then finally, we have the V-hat channel. This one, the scale was actually 3.75 millimeter plus or minus instead of 1/2. But as you can see, the tools don't change too much for what you're doing. And again, if you have a limited run, or the requirements aren't super high, this is a great option for what you're trying to do in your factory. I have a few slides left, and then we'll open it up for questions. And these are exciting because these are real world applications. So these are in automotive companies. This one's from Ford, and they talked about this in a paper, I believe, that was published a few years ago. But this is a Ford fixture for one of their automotive lines. As you can see, there's a lot going on here. The aluminum frame is welded together. There's two orange handles for the operator. There's some vacuum channels to actually suck down the part as they move it around. This tool also has Delrin touching details, so it doesn't scratch the glass or the part. And this tool weighs 12.5 pounds, which doesn't sound like a lot, but imagine picking up and putting this thing down, you know, dozens and dozens and dozens of times per day. So you're looking at ergonomic issues, you're looking at potential risk of injury and carpal tunnel and things like that. And safety is paramount when you're in a manufacturing space. So there's a lot going on here with this tool, and we actually redesigned this to showcase some of the benefits. So I apologize, the images aren't quite big enough on the screen, but hopefully it gets the message across. So we were able to cut the weight down to 9 pounds, so 30% weight savings. And then we were able to reduce the cost by 50% savings versus the traditional labor-intensive welding the tool. And a lot of that was because it was 30 hours to build the tool and weld it up, and a 4 to 6 week lead time in the fab shop. Whereas we were able to print this, you know, in 30 hours, which is far quicker than the 4 to 6 weeks. We were also able to add other features. So we added some dial indicators and damage protectors in there. And of course, we still have metal inserts and things like that. So all the inserts are heat staked and added to the main suction cup tube for accessibility. It was just created to make it more ergonomic for the operator as well. So all in all, it was a really good showcase of how you can take these really complicated assemblies. I'll go back one slide. So this is 29 pieces, and we brought it down to one printed part with you know, some of the other assembly components added. So basically bring it down from 1 month of lead time to 30 hours. So you're looking at some serious cost benefits provided. And this is just one example of hundreds of thousands of examples. So I challenge you again, think about where your tools can be redesigned from something like this to something like this. And then finally, before we open it up to questions, so this is an end of arm tool. Again, this is another automotive application. This is an OEM. And the tool you're looking at, I know it's a little noisy, but the tool you're looking at is a 168 pound end of arm tool used to lift a 15-pound part, which seems crazy, but a lot of times, you know, these end of arm tools are made out of metal. There's a lot of components. So even though your load is only 15 pounds, the robot has to pick up 168 pounds plus the load of the part. And this causes a lot of inefficiencies along the way. So we redesigned this, and we were able to cut down the weight savings from 168 pounds to 68 pounds. And we were also able to increase the cycle time. So if you think about some of the benefits that keep on giving, if you have a heavy end of arm tool, you need a bigger robot, and bigger robots don't move as quickly because of all of the inertia. So the fact that we were able to cut down the weight by 100 pounds means you can buy a smaller robot, which means you can buy a cheaper robot. And the smaller robots move 20% faster per day in this example than the big robot. It also means that you can buy multiple robots, so you can increase your production exponentially, all just because you reduce the weight of the end of arm tool. Now, as you can see, there was a lot of consolidation of the design as well. In the upper right side, you can see some of those diamonds to incorporate self-supporting features and just consolidate it into a few assemblies. So again, to conclude, if you owned a printer on your line, this tool would cost you around $1,600 to print, which is almost a 30% savings versus your traditional fabrication techniques. So that's going to wrap it up for me. I know there's a lot to process. We have a significant amount of design guides, use cases, best practices on our website. If you go to stratasys.com and you look under the materials and applications and support tabs, there's all sorts of content to ensure your success. And we have a lot of really smart, talented engineers on our team just constantly working with customers like yourselves and potential customers to walk you through the process. If you need someone to walk through your factory floor and give you inspiration, or if you need someone to help you quote a part, or just figure out even if your application is feasible, we're just a phone call or email away. But the thing that I want to have you take away is that FDM is just another tool in the toolbox. And if you think differently about how to design and use your parts, you can get tremendous value out of this technology. And especially in times where manufacturers are under constant pressure to retool and just change their lines up and down, this is a great avenue for some really versatile materials and capabilities that should hopefully ensure your success. So with that, I just want to thank you all for joining me, and we'll open it up for questions that I can hopefully answer. Thank you.